Section 7.3 is about the basic counting principles. So the addition principle applies if you're reading a word problem and you see the word or. If it, for example, says, what is the probability of drawing a queen or a heart? That's going to mean that you need to add those probabilities together. So, in the case of something like a queen and a heart, there's the possibility, if you're looking at a standard deck of cards, that you're going to have a queen of hearts in there. So think about it. If I add up all the queens, count those, and I add all the hearts to it, I've actually counted the queen of hearts twice. So if you look at this right here, this explains if I want to find the number of items in either set A or set B when it's a union. And in this case, let's say we wanted to know the number of queens or hearts, then you can take the number of queens plus the number of hearts, and notice here at the end, you would subtract out any card that is both a queen and a heart. Okay? Now, if the two things are disjoint, it means they can't happen at the same time. They don't have anything in common. Then if you're trying to subtract out the part that's at the end, it's going to be 0 because there won't be anything in both sets. So basically it just simplifies that formula for you. Now, if I'm reading a word problem and I see and I wanted to know what's the probability of getting a queen and a heart, then it means both of those things have to happen at the same time. And in that case, there would be only one card. But suppose I said, what's the probability of maybe rolling a 3 on a die and drawing a queen? Well, I could calculate the probability of rolling a 3 when I roll a single die, and that would be 1 out of 6. And then the probability of drawing a queen would be 4 out of 52 cards in a deck. And because I want to know the probability of both of those, because it said and, I would multiply those together. Okay, so if it's an or statement, you add. If it is an and statement, you would multiply. Now, in order to figure out the number of ways that you could take the set of numbers 1, 2, 3 and show the possible outcomes, you would need to list the way that all of these could be arranged. Okay, so if we were to list them, we would have the way that it appears: 1, 2, 3. That's one possibility. I could also have 1, 3, 2. I could switch the second and third items in my list. I now have come up with every way I could write this set if 1 is the first number. So now I'll use 2 as the first number. So I could have 2, 1, 3. But I could also have 2, 3, 1. And that takes care of every possibility of 2 as the first number. Then I could have 3, 1, 2. But I could also have 3, 2, 1. And at that point, as long as I'm using all of those elements, because if it says you're going to take that set, list the ways it can be arranged, I've covered every possibility. Now, the nice thing is there is something that's called the counting principle that is a quick way to figure this out without having to list all of the items. Now, the next one says you could use a tree diagram, and that's fine. If you did that, you're going to create a little visual aid. So I know for the first digit, I could have either a 1, a 2, or a 3. All I would do is then map out, if the first digit's a 1, the next digit could be a 2, or it could be a 3. And I could go through and identify all of these possibilities here for the second digit. And then I would show what would happen on the third digit. If I've already used the 1 and the 2, the third digit would have to be 3. This would have to be 2, because remember, I can use each digit only once. And then that one would be a 3, this one would be a 1, this one would be a 2, and this one would be a 1. And then I could count up. I'd have whatever number of digits I have in this third column will tell me how many different ways I could arrange it. Count them up. You have 6 ways, which is the same thing we got when we listed them out. There were 6 ways. But the easiest way to calculate this is to use the multiplication principle, which simply says this: if I look at the numbers in that set, how many different choices do I have for the first digit? Well, there are 3. Because I could either use 1, I could use 2, or I could use 3. Now for the second digit, remember I have to use each one time. So I've already picked a number. I don't exactly know what it is, but one of them is gone. How many does that leave me for choosing the second digit? Only 2 options. And then that means for my third digit, I've got to use whatever number is left over. So if I'm having to choose 3 digits, I could draw these 3 blanks, and that means my first choice, I had 3 options. After I pick one, I only have 2 that goes in the next blank, 1 in the last, and if I multiply these together, guess what? I get 6. That's exactly what we got when we either used a tree diagram or we listed out the sets. So using the multiplication principle is a great time saver once you understand how it works. Let's go to the next slide. All right, so Carol picks out a birthday gift for her younger brother, decides to have it gift wrapped by the store. So she has some choices. She can have 3 different kinds of wrapping papers, either plaid, stripes, or checked. And then she's going to pick a ribbon. She's got 3 choices for the ribbon. It can be red, green, or yellow. Now, the first thing it asks you to do is to determine the number of ways she can have it gift wrapped using a tree diagram. Now, I'm going to show you one more time the tree diagram. After that, we'll just start using the counting principle. So, for the wrapping paper, what were her options? Well, it said she could have plaid, she can have stripes, or she could have the checked wrapping paper. Now after that, she's got to pick a ribbon. And she has 3 different options for ribbon colors, either red, green, or yellow. And that's going to happen for every one of these different, remember this is just what we're doing here. So here's your choice. If it's plaid, it's red, green, or yellow. If she went with the striped paper, then she's either going to choose a red, a green, or a yellow ribbon. And if she went with the checked, she's going to have a red, a green, or a yellow, because these are our ribbon choices. All we have to do now is count up in this column right here how many different letters we see representing the ribbon colors, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9. She has 9 ways that she can choose to have that gift wrapped because she had 3 different options on the paper and 3 different options on the ribbon. But isn't it much easier to say she's got 2 choices? Choose paper, choose ribbon. She has 3 options for the paper, 3 options for the ribbon. If I multiply those together, that tells me there are 9 ways that she could choose to wrap that gift. So much simpler. Okay, talk about Joe and Fred for a moment. They're going out to dinner at a local restaurant. On the menu are listed 4 different salads and 7 different entrees. Joe's not feeling very hungry, so he decides he will have either a salad or an entree. I'm going to circle the word or for a minute. Fred, however, is ravenous, and he decides he will have both a salad and an entree. Now, let's figure out how many choices does Joe have if he chooses a salad or an entree. What did we say needs to happen when we see the word or? Do we multiply or do we add? Or tells me to add. So Joe is going to have how many choices for salad? If I go back and I read, there are 4 different choices for salad. How about for an entree? He has 7. But since he's only going to choose a salad or an entree, we add those together. And that means he has 11 options on what he would have for dinner. Now Fred, on the other hand, is going to choose a salad and an entree. So he still has 4 choices for the salad. He has 7 choices for the entree. But since he's having both, and we saw the word and, we're going to multiply. There are 28 different ways that Fred could put together his meal. Let's go to the next slide. This example is a little bit different. I wanted you to see it because I think you're going to see something similar to this in your homework. Notice it says the 14 colleges of interest to a high school senior include 6 that are expensive. That means the tuition is more than $30,000 a year. And 7 that are far from home, which would be more than 200 miles away. And then there are 2 that are both expensive and far from home. So if the student decides to select a college that is not expensive and within 200 miles of home, how many selections are possible? Now, notice, think for a moment. I know we see the word and, but how many different things are you choosing here? The answer is you're only choosing one thing. You're choosing a college. So this is not going to be something that you multiply. Instead, you're going to figure out how many colleges would fall into the category of being not expensive and being within 200 miles of home. So let's think about what they've told us. Okay, there are 14 colleges in all. Now, if we look back, we know 6 are expensive, 7 are far from home, and there are 2 that are both of these. Now, think about what we've learned. Is there some overlap here? Do we have something that's being counted in both groups? And the answer to that is yes. These 2 colleges that are both expensive and far from home have been counted in both of those groups. So here's how I would calculate how many of the colleges are either too expensive or they're far from home. We would take the 6 that are expensive plus the 7 that are far from home, and that gives us 13 out of the 14. But since 2 of these have already been counted in both places, we subtract 2 from that. And that leaves us with 11 that are expensive or too far. Now, if there were 14 colleges being considered, and we want to know how many could the student choose from if the student is choosing one that's not too expensive or not too far, wouldn't that have to be all the colleges that didn't fall into this group of 11? And the way we find that is to subtract it from the original 14. That means there are 3 colleges that student would then choose from. All right, number 5. A survey was done by the local humane society at a shopping mall. The survey asked 200 shoppers if they owned a dog or a cat. The survey found that 80 people owned a cat, 55 people owned a dog, 23 people owned both a dog and a cat. How many people in the survey owned neither a dog or a cat? And then how many people owned a dog but not a cat? Well, we're going to need to do a little calculating to figure that out. So here would be the way you would want to do that from looking at this diagram that we've been given. So what it tells us is this. The survey asked 200 shoppers, that's told to us right here, to answer whether they owned a dog or a cat. So I know 200 people were surveyed. What I'm trying to figure out would be, if this represents right here how many people just owned a cat, and this represents how many people just owned a dog, and this is how many people owned both. Out of these 200 people, how many owned neither a dog or a cat? Well, wouldn't that have to be everybody that's outside the circle that's C or the circle that's D? Absolutely. So this right here is going to be the number of people who owned neither. So that's the first question. Now, the second question is, how many people owned a dog but not a cat? Well, that would have to be everybody that's in the D circle but is not in the overlap where the D and the C cross over. And that would have to be 32 that owned just a dog. So if you're given the diagram along with the information, that's pretty simple to figure out. Sometimes, though, you may be given the information and it hasn't been placed on a diagram. So I want you to look at this and let's see if we could figure out how to place this information on the diagram so that we would be able to answer a question about it. Now, the first part of the question that we see, or actually not question, but just the information we've been given, is that the number that would be in C is 70, and this is telling us that in just C, there's going to be 70 here. Now, the number that's in just L is going to be 40, and the number that's in the intersection of C and L is 25. And the number that's in the entire set is 140. Now here's where you have to be careful. That doesn't mean 140 is down here in the corner, because that would not be everybody that's already in the set. I need to add up how many are already there, and when I subtract that number from 140, that's what will go down in the corner, the ones that are neither in C or in L. So if I take 70 plus 40 plus 25, add that together, I get 135. And if there is 140 total in this union, this entire set, then that would tell me 140 minus 135 means there are only 5 that are outside all of those circles. Let's go to the next slide. Okay, now we have, instead of a Venn diagram, we have a table to fill out. So remember what these symbols mean. We have a column for all of the elements that are in A. That's right here. The apostrophe after the A means A complement. It's just saying not A. So this would be the total of everything that's not in A. And then we have a third one that is just going to total up everything that comes across in these rows. So we also have these rows that are going to tell us everything that's in B and everything that is not in B. And then we have a row of totals to total up our columns. Now, let's see if we can figure out where to place all the information. The first thing we're told is that the number that's in A, if I had the total of everything that's in A, that's 70. That's got to go right there for that column that's 70, because anything that's in A, if I add it up, it should equal 70. Now, the number of items in B would be 90. So if I look where B is, I'm going to go across until it says total, and that's where I'll put 90. If I add up everything that's in B, it's got to equal 90. Now, this one is the number that's in the intersection of A and B. Well, where A and B intersect would be the box in the table where the column for A and the row for B meet. And that's this one right here. This box is going to be the intersection of A and B, and that has a value of 30 according to the information we've been given. The last piece of information is that the entire set should have 200. Now, where I'm going to place this on the table is if I add up everything in this column and in this bottom row, it ought to total up to be 200. Now, that's the information that I was given. Notice I've got blank spaces, but I can go back and figure out what goes in these blank spaces by using a little bit of subtraction or addition. So if we look at column A, we know we have 30 here. What we don't know is how many are in B complement, this right here. But I know if I add this plus this, it should equal 70. So what would 70 minus 30 be? That's 40. And I can fill that in. Let's look at going across, and what I know is there are 30 that are in both A and B. What I don't know is how many are not in A, are in A complement and in B. But I do know that if I added everything that's in B, it's going to equal 90. So if I subtract 90 minus 30, I'm going to get 60. That's what goes in that box. Get the idea? Okay. I would now maybe come over to this box. And what I know is that I should be able to add the 90 that I have plus whatever is missing in this box, and it would equal 200. Well, if I take 200 minus 90, that's going to give me 110. Okay? The other missing boxes, I complete the same way. This one, I find if I do 200 minus 70, that's going to be 130. And then I can either use my column, which is A complement, to find this one, or I could use this row, which is B complement, to find this one. And I ought to double check myself. If I do it one way, I should do it the other, just to make sure that all of these values are working out. If I did 110 minus 40, that gives me 70. And I check that by asking, is 60 plus 70 equal to 130? And the answer is yes. I now have those totals complete for this table.